All right, so welcome to the first in-person class of multivariable calculus. This is lecture 4. And what I want to do today is just talk a little bit about reviews of Calc 1, Calc 2. There was a request to do one type of integration problems. I did some differentiation review in Calc 2 earlier today, so I'll make those slides and notes available. We just went through how do you do a really painful derivative. And what's nice is I can't give you a derivative that you are unable to do. You can just hack away, just keep using the rules. Is it a sum? Okay, let me use the sum rule. Is it a product? Let me use the product rule. It may take a while, but you will eventually get it. Integrals are completely different. It is very easy to write down an integral that we can't evaluate in closed form. But there is no excuse for writing down an incorrect integral in my class. Why is there no excuse for writing down an incorrect integral? What can you always do once you have your integral? You can test it. How would you test it? You take the derivative. And so you can take the derivative, and if it works, okay, good. I suggest you, when you do that, don't look at what you've done, take a new piece of paper and just look at that. It's very easy to make a mistake if you have something in front of you. I sent you the article by Isaac Asimov on the planet that wasn't. And when you have a thought of what the data should be, it will often color the path you take. Normally, my cell phone policy is if your cell phone goes off in class, you have to provide breakfast for everybody the next day. But I believe we are still at the point where we're not allowed to be eating in class. So instead, if your cell phone goes off, everybody gets a quiz, and they know that it's your fault that there's a quiz. My cell phone is 617-835-3982. You're welcome to have your friends try to call me during class. If my phone goes off, then you all have one in the bank where if someone's phone goes off, it cancels that. So rather than having anybody bring food, what I will do is I will bring chocolates. And you are welcome to take a chocolate after class if you make a comment in class. If you are hungry and you are not going to be able to get lunch for a while, you can take some chocolate in advance and just owe me a couple of comments during the class. I really want you to get in the habit of speaking up, even if you think the problem is straightforward. And the reason is, the more you speak up now, the more you'll speak up in later classes, and the more likely you will be to be noticed in the future. And it's just a habit. The more you do, the easier it is. When I was young, it was extremely hard for me to speak up. So I will talk a little bit about matrices and vectors as time permits towards the end. If there's anything in particular people want to see, just email me before class. We're going to start with the real lectures on Monday. And you will start talking about vectors and notation. So it's always an interesting question, which class should you do after Calc 2? Well, we did Calc 2 after Calc 1, Calc 3 after Calc 2. That seems to make sense. You could also make an argument that you should do linear algebra. Is that to do Calc 3 properly, when you have things with several variables, it helps to know matrices and how to move things around. It helps to be able to think about things in multidimensional space. Some schools actually have a combined multivariable calculus linear algebra class where you start doing a little bit of linear algebra, then you do some calculus, then you do linear algebra again, and you see the interplay between the two. So if you take linear algebra after this, you will then get to see a lot of connections and additional things. I will talk about some applications of linear algebra in places. If you're not comfortable with linear algebra, absolutely fine. But I want you to get a sense of where it comes from. Probably the biggest day on that will be when we do the method of least squares or linear regression. You're trying to find your best fit lines to data. And I will talk to you about some of the real world applications I have done. And there may have to be some equipment malfunctions as I talk about some of that because it's being recorded. All right. So let's just do some integration review. So there's a lot of different techniques. And so the first is u-Substitution. And what you need to remember is every time you have an integration rule, where does it come from? Well, if you remember the log laws, all the log laws come from rules of exponents. And there's this conversion factor from exponent laws to log laws. It's the same thing with calculus. All of the rules from integration come from rules from differentiation. So u-Substitution is really the chain rule. If I give you f of g of x, and I ask for its derivative, it's just f prime of g of x times g prime of x. Okay, well, what does that mean? Well, it means if I integrate, say, f of g of x dx, and I take the derivative of this, That's the same as integrating f prime of g of x times g prime of x dx. So if you're fortunate enough that somebody gives you an integral where you can write the integral as a product in such a way that the first term is the derivative of a function you know evaluated at the second, at the antiderivative of the second term, then you can just immediately write down the answer. So the question is, when can you notice this? And so much of math all comes down to how do you notice this? So I'm going to stop the video for just a second, and then hopefully you can see this on the screen. Let me stop this. Okay, so hopefully you can see this on the screen. Okay, wow, it's just having an incredibly long lag, incredible, to get from here to there. All right, what is this? Rubik's Cube. It takes me about an hour to teach someone how to do a 2x2 Rubik's Cube. If people are interested, we can have a Rubik's Cube day at some point. How many sides? 6. How many pieces on each side? 9. Okay. This is also a Rubik's object, but I don't know if we'd call it still a cube. How many sides? How many pieces on this side? 9. And on the opposite side? And on these sides? So it looks different. And so if I try to turn the red side, as I normally would, I can't turn it. So does this look much harder? Is there anybody here who's really good at Rubik's Cubes? Okay. This is actually almost identical to the regular cube if you look at it the right way. If you look at it at a 60-degree angle, so I can try to hold it just right, I can now turn this side, and this is the whole side, and there's my 9 pieces. It's written in such a way to hide what's going on. But if I go like this, it's essentially the same as a regular cube. The only slight difference is in a normal cube, the sides all are just uniform colors. And so if the center was turned 90 degrees, you would never notice it. If you put pictures on the cubes, that's what corresponds to here. But other than that, they're essentially the same. The same methods that solve a 3x3 solve this if you know how to look at it. And to me, this is the best way to really drive home what we're going to try to do in this class. It's all about finding what is the right way to look at problems. I am not expecting any of you to become professional multivariable calculusists. It's not even a career, right? It's also the 21st century. We have computer programs that can do integrals and areas and stuff like that, that can do derivatives. What I want you to get out of this course is how to look at problems, how to model things, how to conjecture, how to come up with ways to apply mathematics in important settings. That's going to be extremely valuable. So here, okay, great. I've got the chain rule. I have a rule of integration from it, but I have to recognize that I have something of the form f prime at g of x times g prime of x. How am I going to recognize that? And the idea is u-substitution. So let u equal g of x. Then what would du dx equal? That would just be g prime of x. So in a slight abuse of notation, let's say du is g prime of x dx. And so now our integral of f of g of x prime d of x is just the integral of f prime at u, because g of x is u, and then g prime of x dx is just du. Let's make it a little bit more explicit. Let's say x goes from a to b. So x goes from a to b. X goes from a to b. Would I still write on the final integral x goes from a to b? Is my final integral an integral over x? No. What do I do? I've got to figure out what is the range for the final integral. Yes. Yeah. And so I would start with u equals G of A, and it goes all the way up to G of B. Okay, this is perhaps the nicest derivative I could give you. Or sorry, the nicest integral to give you. I want you to find the function whose derivative is f prime. What function has derivative f prime? F. So this would just be f of u evaluated at g of b and g of a. So that's just f of g of b minus f of g of a. And if you think about what we have on the other side, well, we have the integral of the derivative of f of g of x. What function has derivative f of g of x? It's just the function f of g of x. So this would just be f of g of x at x equals a and b, and that's going to just be f of g of b minus f of g of a. So this is where the u-substitution comes from. It comes from the chain rule, and the whole point is I'm trying to detect when I might have something of the form f prime at g of x times g prime of x. So have I done the newborn baby metaphor in this class yet? Okay, so when I first taught differential equations at Williams, my daughter Kayla was born shortly into the semester. So if you have a newborn baby, the baby is crying. Why is the baby crying? What are your possible reasons? Hungry, yes, good. What else? Life would be very simple if that was the only reason baby's crying. Tired. You got to do better, otherwise I'm really worried about the next generation of legacy kids. Sorry? Got hurt. Hopefully not by the new parent, but yes. Hurt. What else? Looking for attention. But there's lots of reasons why a baby can cry. And at first, when the baby is crying, you don't know. So what do? Yes. Sadly, yes. Good. You just it's utopia. Try anything. Try everything. Keep going down the list and hope that at some point you hit what will soothe the baby. Right? And after a while, after you've been a father or mother for a while, what do you start to notice when you hear a cry? Ah, that's the hungry cry. That's the I want to be held cry. That's the I need a new diaper cry. Might be a little scary that nobody thought about that one, but I forgot about that myself. Anyway. So you start to recognize which one it is, and you can just go straight to them. But in the beginning, when you're not sure, you just try everything. So when you're trying to find derivatives or antiderivatives, just go through the list. And sometimes as you start to build up your intuition, you can just jump in, oh, this is a u-substitution. You can't disguise that. So what do you think the problem I'm about to show you is going to be? Probably a u-substitution, just because I just did the theory of u-substitution. So let's say I have the integral, x goes from 0 to 1, x cubed e to the 2x to the 4th dx. Okay. Now you might ask, why am I writing x goes from 0 to 1? This is not like Charles Dickens. He was paid by the who knows who Charles Dickens is? This is Williams. You got to know, okay, who's Charles Dickens? A lot of stuff. We have a lot of words from him. Scrooge comes from. Okay. Can anybody quote the beginning of? Yes. Yeah. It was the age of wisdom. It was the age of ignorance. It goes on and on and on like this. Charles Dickens was paid by the word. Right? He was paid by the word. It was, could have just said, it's 17 whatever. Now, there's nice literary reasons as to why we'd be doing all of this. Why am I writing x equals 0 to 1? I'm not saying that I am as good as Charles Dickens, but I'm probably doing this for a reason. Well, this is multivariable calculus. Eventually, we're going to have several variables in play. I want to get in the habit of when I write down integrals, I tell you which is the variable at play. Because eventually we're going to have more than one. And so if I just get in the habit of writing x equals, oh, okay, I'm integrating with respect to x. And eventually we're going to have more variables. The more I write things down, the easier it's going to be. Never, ever, ever pass an opportunity to make things clear to the reader. How many people write programs or do coding? How many people put in comments? If you put your hand up for the first, your hand should still be up for the second. You want to make it easy for people to read and follow. So put in stuff. X goes from 0. All right, so when I'm looking at this, I'm trying to think, is there a u-substitution? Is there a good choice of u? When I look at e to the 2x to the 4th, I'm thinking, okay, I've got e raised to the 2x to the 4th. What's the derivative of 2x to the 4th? Okay, so it's 8x cubed. Which is the important part, the 8 or the x cubed? The x cubed. I can always adjust for a constant factor. Constant factor is not a big deal. The x dependence, that's the big deal. So I might try u equals either x to the 4th or 2x to the 4th. I have a choice. I'm going to go with 2x to the 4th because then it's going to make my exponent really nice. So just e to the u. So if I have u is 2x to the 4th, du dx is just going to be 8x cubed, or du is 8x cubed dx. You don't have to put in this step in the middle if you don't want to. You can just jump to u equals 2x to the 4th, du is 8x cubed dx. But when you look at what we have, I can rewrite this as the integral x goes from 0 to 1 of x cubed, oh, sorry, not x cubed, e to the 2x to the 4th times x cubed dx. That looks almost like what we have, right? So there's a couple of ways we could go about this. One is I could multiply this by 8 and then divide by 8. So I have the 8x cubed dx. Or I could just say, since I have x cubed dx, I could just say 1/8 du is x cubed dx. And now that's designed beautifully to substitute in. Or again, I could up here, I could multiply by 8 times 1/8. It's all about trying to do the algebra, trying to see things. So now I have the integral x goes from 0 to 1, x cubed e to the 2x to the 4th dx is the integral u equals, and so now when x goes from 0 to 1, what does u go from? So 0 to 2. And I think I wrote u not. And so now u goes from 0 to 2, and then e to the 2x to the 4th just becomes e to the u, and then x cubed dx becomes 1/8 du. So that's just 1/8 integral u goes from 0 to 2, e to the u du. Well, what is the antiderivative of e to the u? E to the u. So it's e to the u evaluated 0 and 2. So it's 1/8 e squared minus e to the 0. E to the 0 is 1, so I just get e squared minus 1. Okay. And so this is how you would do a u-substitution. The challenge is figuring out, what should I try? The more complicated the function is, in some sense, the better. Because if it's really complicated, the only way it's going to work out is if everything aligns. And so when I see I have e to the 2x to the 4th, there's no nice antiderivative of e to the 2x to the 4th. It needs an x cubed by it. Oh, good, I have an x cubed. Yes.
How do we know that?
Okay, so u equals 2x to the 4th. And so when I plug in, when x equals 0, I get 0. When x equals 1, I get 2 times 1 to the 4th. Now, one of the things you have to be careful about in problems like this is that when you do these substitutions, it has to be a one-to-one change. So for example, let's say I integrate from 0 to 1 No, that's not it. Let's do -1 to 1 of x squared e to the negative x cubed over 3 dx. What should I take u to be? Yeah, actually, but let's make it a positive x cubed. I don't want to deal with a minus sign. It's been a long day. So we'll make it x cubed over 3. What will du dx be? X squared. Du is going to just be x squared dx. So you can see I'm just trying to make my life easy. I don't even want to deal with the constants anymore. I did it once. So we now have the integral. X goes from -1 to 1 of x squared e to the x cubed over 3 dx. And now x goes from -1 to 1. What does u go from? I'm sorry? -1/3 to 1/5. Okay. And so I integrate, I have u equals -1/3 to 1/3 e to the u du. So it's going to become e to the u at -1/3 and 1/3. So it's e to the 1/3 minus e to the -1/3. Do you think this is right? It's the 21st century. What could we do to check? Well, we're finding a number. So if we take the derivative of a number, we get unfortunately 0. An integral calculator. And in a remarkable coincidence, I might actually even have one loaded up right now. I do. What a coincidence. So let's actually integrate. So this is Mathematica. You can also use Wolfram alpha on lines terrific. So I'm going to integrate. Is this large enough that people can see? My eyesight is going, so I can see it. I figure based on my distance, and where your distance is not too bad. So I want x squared exponential of x cubed equals -1 to 1. Let's see what the answer is. So it's 2 hyperbolic sine of 1/3. All right, so I actually know what the hyperbolic sines are, but let's just multiply by 1.2, so it gives me a numerical value. Yes. It means e to the x cubed over 3. Yes. And now the answer we had was we had exponential of 1/3 minus exponential minus 1. Do you think we got it right? Now this is only reporting a couple of digits of accuracy. I can report more digits of accuracy and it will work. And in fact, Mathematica gave the exact answer. It gave the hyperbolic sine. We talked a little bit about hyperbolic sine at the end of the last class. The hyperbolic sine actually go in this case twice, so that will actually do e to the 1/3 minus e to the -1/3. So we actually do get it correct. All right, so far so good. We're doing well. Let's do one more problem. Let's do one more integration by u-substitution. Let's integrate from -1 to 1 of x e to the x squared over 2 dx. So what should u be? X squared over 2. And what should du dx be? It should just be x. So du is going to be x dx. And as x goes from -1 to 1, where does u go from? Not 1/2 to 1. Okay, yes, it goes from 1/2 to 1/2. So this should worry you a little bit. We had a nice full interval. And now we have just a point. So this is going to give us the integral from -1 to 1 of x e to the x squared over 2 dx is equal to the integral u goes from 1/2 to 1/2 e to the u du. What does that integral equal? 0. It turns out this does equal 0. It's an odd function on a region symmetric about 0. So whenever you have a positive value of x, the contribution there is perfectly balanced by the contribution of the negative value of x. So it does give you 0, everything works. But just because things check out does not mean you've done everything right. Any physics people here? I know we have a few. Have you done problems with refracting between two different media? So when I was in high school, I took a physics class at Harvard. I was actually happy when I went to Yale and they said we don't consider a class from Harvard as acceptable. And so I actually made 2 mistakes on one of the problems. I was off in my orientation by -9. But because I was off in both of them, the mistake then actually reinforced itself and canceled out. And the grader only checked the answer, because if the answer is right, then I don't have to look at your work. And so I actually got full credit for making 2 mistakes in the calculation because they canceled each other out. So you have to be careful. Just because you get the right answer doesn't mean you have the right logic. The problem is we should not be reducing the entire interval -1 to 1 down to a point. What's going on here? Well, if you look at u equals x squared, if I plot things, here's x, here's u. If I give you a value of x, it does give me a value of u. That's good. But the problem is, if I give you a value of u, there are 2 values of x that it can come from. And so you have to be careful when you're doing u-substitution that you always have, for each value of x, there's one and only one value of u. In the last one, we had x cubed over 3. For a cubic function, when we plot that, it's going to look something like this. And so, given a value of x, there's going to be one and only one value of u. And so everything is going to work out in this case. So just have to be a little bit careful about this when you're doing u-substitution. Any other integration techniques people want to practice? Integration by parts. So integration by parts. So this is the other one we really need to know. And again, all of these rules come from rules of differentiation. So where does this one come from? It comes from if I give you f of x, g of x prime, this is f prime of x, g of x, plus f of x, g prime of x. So I can rewrite this as f of x, g prime of x equals f of x, g of x prime minus f prime of x, g of x. And so if I integrate from, say, a to b of f of x, g prime of x dx, this is the integral from a to b of f of x, g of x prime dx minus the integral from a to b f prime of x, g of x dx. Well, the first one is one of the easiest integrals to do. I want to integrate the function whose derivative is f of x times g of x. So what function has derivative, the derivative of f of x, g of x? So I want a function whose derivative is the derivative of f of x times g of x. Which is f of x times g of x, right? So the antiderivative of the derivative is just the function. So it's just going to be f of x, g of x at a, b, minus the integral from a to b of f prime of x, g of x dx. So this is integration by parts. The only thing that we do is we let u equal f of x, we let v equal g of x, dv is g prime of x dx, du is going to be f prime of x dx. And so when we use that notation, then the first integral just becomes the integral a to b of u dv equals uv at ab minus the integral from ab of v du. So this is where the integration by parts formula comes from. It comes from the product rule. And the whole point is we just want to use this to convert from one integral to another. Now, when you look at the right-hand side has two terms. This term over here, this is just ub vb minus ua va. Okay, that's not bad. It's just evaluating the functions of 2 points. I'm not worried at all about doing that. So what this basically says is, I'll make a deal with you. Instead of integrating u dv, instead of integrating f of x g prime of x, instead, how would you like to integrate f prime of x g of x? You can switch which function has the derivative at a cost of a minus sign and this boundary term. That's what integration by parts is. It's which integral would you rather do? The more complicated your functions are, the harder it's going to be to do integration by parts because you have to figure out which way to combine things. So let's do an example. So let's integrate from 0 to 2 pi of x cosine of x dx. So I have to choose what do I want to be u, what do I want to be dv. The simpler the function, the fewer the choices. So what are my choices for u? So I think there's two natural choices. X and cosine of x. Which do you think is a better choice, x or cosine of x? X, why? Good. So right now, if I didn't have that x there, I would just have the integral of cosine. Oh, I know what the integral of cosine is. That's not a big deal. Well, at least I should know. The x is making things complicated. If I had dv equals x dx, then v would be x squared over 2. Oh my God, it's making it worse. It's going in the wrong direction. So it's much better to take u to be x. Fortunately, if you make the wrong choice, what can you do? Do it again, right? If there's only two choices. So what you can do is, let me start doing it this way. And after a while, if I see I'm stuck, let me put this off to the side, take a new piece of paper, well, I guess this is the 21st century, take a new computer screen, and work on it the other way. And if you see that that's even worse, then go back to the first approach. But when there's only two possibilities, try one for a little bit. If it works, great. If not, go back. So I'm going to try u equals x, dv is cosine x, du is going to be dx, and then v, what function has derivative cosine? Sine. And so the derivative of cosine x is minus sine of x, and the mnemonic is minus sine. And the derivative of sine of x is cosine of x. One way you can see this is if you look at the unit circle, here's the point cosine theta, sine theta. And so if I start off at theta equals 0, cosine is 1 and sine is 0. As I increase theta from 0 and gets larger and larger and larger, cosine is getting smaller, sine is getting larger. If your function is getting smaller, what's true about your derivative? So what can you tell me about the derivative if you're getting smaller? It'll be negative. And if you're getting larger, what can you tell me about the derivative? positive. So because cosine is getting smaller, it needs a negative derivative. Well, sine is positive in the first quadrant. So the only way it can work is if it's minus sine. So what's nice is I don't have to completely rederive the derivatives of sine and cosine if I forget them. If I remember one of them has a minus sign, but I can't remember which one, I just have to look at a few special cases. If you remember the second derivative test, to try to find if you have a maximum or minimum. Well, if I look at the parabola y equals x squared, its second derivative is 2, that's a minimum. If I look at the parabola negative x squared, its second derivative is negative, that's a maximum. Okay, so the positive second derivative goes with the minimum, the negative second derivative goes with the maximum. I can get that by looking at special cases. So here, I would now have, okay, so the integral from 0 to 2 pi of x cosine x dx is going to be uv, so that's going to be x sine of x at 0 and 2 pi, minus the integral from 0 to 2 pi of v du, which is just going to be sine of x dx. What's the boundary term x sine of x at 2 pi and 0? So it's going to be 2 pi sine 2 pi minus 0 sine 0. Okay, 0 sine 0 is clearly 0. What's 2 pi sine 2 pi? What's the sine of 2 pi? Come all the way back to the beginning of the circle. It's just 0. So these bounds were chosen to make it nice. So this is just going to be negative the integral from 0 to 2 pi of sine of x dx. What function has derivative sine of x? I'm sorry? Not, well, it depends which question you answer. What function has derivative sine of x? Negative cosine. But we have a negative sine of x. So because we have a negative sine of x, the antiderivative of sine is negative cosine. The negative reinforces the negative, and we are left with cosine of x at 0 and 2 pi. And what do we get? We get cosine of 2 pi minus the cosine of 0, which is 1 minus 1, which is 0. Okay? And so this is how you would do integration by parts. The more involved the function is, the more choices you have. I am not going to do examples in this class really where we need to use partial fractions. You should be aware of that technique. If you take differential equations, you will have to refresh yourself on it. But the purpose of this class is not to overwhelm you with painful derivatives and integrals. So years ago, I was a graduate student at Princeton, and I was teaching multivariable calculus. And at the end of the year, I asked the students, how they liked the course and how they liked the problems. And as your graduate student, you don't really get that much choice in terms of what you do, but you have a little bit of a choice. So they had problems such as you have two cylinders intersecting at right angles. They have the same radii, they intersect perfectly. What is the volume of the intersection? And I asked them, how much do you like these problems? And they all hated them. I said, okay, should we get rid of those problems for next year? And what do you think they said? Good. So why did they say no? Okay, we're talking about Princeton students. Okay, in full disclosure, yes, I went to Yale. So they did not say because you learned it. What did they say?
Make the people next year have to do mistakes.
Yes, and why?
Like
We suffered, so they should suffer. And then I smiled and said, I had this conversation last year and the year before. Who can tell me what this is? It's the top left of the typewriter. It's proof that your parents hate you and we don't love you. Why do typewriters start off QWERTY? Yes.
because these two typewriters, so you have to get that.
Right, because they would actually have the things going down and hitting the paper. And if you hit two keys in quick succession, they would jam. The typewriter was designed in terms of the choice of the letter location to slow you down. Okay. I don't think this is a real issue anymore in the 21st century with these computers and our devices. Straight alphabetical is better. Dvorak is what the professional typists use. Why do we still use not everyone, the people who haven't learned aren't used to it, but the people who are in power, old people like myself, we are used to the QWERTY keyboard. We're going to have to learn a new keyboard now. We've all learned how to use this. It's amazing the inertia things have. The last one is, what does CC stand for in an email? Carbon copy. This goes back to, anybody know what carbon copy goes back to? Old receipts where you couldn't get multiple copies by just printing out another copy. You would have carbon paper and you would just write down hard and it would make 2 or 3 copies. Some people have redefined carbon copy to mean courtesy copy now. All right, so let's do a calculus test. X cubed, x to the 3/2, and let's do x to the square root of 2. So here's the function. And I want to know what the derivative is. So what's the derivative of x cubed? The x squared, excellent. X to the 3/2. We have x to the 1/2 and x to the square root of 2. What's the root of x to the root of 2? One of, okay. X to the root 2. Yes. So the rule is x to the r has derivative r x to the r minus 1. How many of you had this proven to you in a calculus class? Raise your hand. It's not your fault if it wasn't proven. Okay, so I want to say a few words about this. So f prime of x is the limit as h goes to 0, f of x plus h minus f of x minus f of x over h. This is the definition of the derivative. When we do multivariable calculus later, we'll see that there's actually a better definition of this. There's 3 ways to write down the derivative in one dimension. This is the way you're most used to, but it's not the way that generalizes best. But let's do that for now. If I give you f of x is x to the n, f of x plus h is x plus h to the n. This is x to the n plus n choose 1, x to the n minus 1 h plus n choose 2, x to the n minus 2 h squared plus dot dot dot. And this is binomial theorem. This is basically Pascal's triangle. So you could write this in, if you want, as x to the n plus n x to the n minus 1 h plus h squared times crap. I don't really care what the crap is. It's just something involving n's, h's, and x. Something nice. So if I look at f of x plus h minus f of x over h, the x to the n's are going to cancel. I have n x to the n minus 1 h over h. That's going to give me an n x to the n minus 1. And I'm going to have h times crap. As h goes to 0, this goes to what? So what would h times crap go to? 0. So the derivative is n x to the n minus 1. So this is how you would prove what is the derivative of x to the n. One of the things that's extremely important to be careful of when you're doing math is to keep track of what are the assumptions. What am I assuming here? I'm assuming n is an integer. if I now want to do f of x equals x to the 3/2, and I want to look at f of x plus h is x plus h to the 3/2, how do I expand that? We don't have Pascal's triangle anymore. We don't have the binomial theorem anymore. So if I wanted to try to write x plus h to the 3/2 minus x to the 3/2 over h, this is really hard. Now, I will just make a quick note. There is a trick that I can do. There are so many proofs in mathematics that all come down to doing nothing. So there's two ways to do nothing to an equation. How can you do nothing to it? What can I do that won't change its value? Multiply by 1 or add 0. And one of my professors at Yale, Peter Jones, said the log of 1 is 0, so there's really only one thing you can do. If I multiply by 1 in a very clever way, if I multiply by x plus h to the 3/2 plus x to the 3/2 over x plus h to the 3/2 plus x to the 3/2, well, what would I get? When I do that, I get x plus h cubed minus x cubed over h times x plus h to the 3/2 plus x to the 3/2. And now if you continue, now you can analyze the numerator, and the denominator is going to converge to essentially h times 2x to the 3/2. And as a nice exercise, you can finish the proof and you can use this to take the derivative. The point is the derivative of x to a rational power, the proof is different than the derivative of x to an integer. Another way to see the answer is, let's say I give you f of x is x to the 3/2. Let's let g of x be f of x squared is x cubed. And this illustrates a really powerful point, that sometimes it's easier to look at a related function. If I square the function, I now have x to the cubed. I know how to differentiate x cubed. What rule would I use to take the derivative of f of x squared? So what rule would I use to take the derivative of f of x squared? There's two rules you could use. You could use either the chain or the power. And so I would get g prime of x is 2 f of x, f prime of x is 3x squared. So f prime of x is 3x squared over 2f of x. So 3x squared over 2x to the 3/2. So that's 3/2. I have x squared divided by 3/2. That's x to the 1/2. And there you go. As an exercise, do x to the p over q. So this is how you prove the derivative if it's not an integer, but if it's a rational number. And the reason I'm showing this is, one, I'm a pure mathematician who loves stuff like this. The second is to show you how easy it is to accidentally use a result where you haven't proven it. And so when you had your calculus classes, I don't know if the teachers warned you that the proof that they gave you, if they gave you a proof even, only works when n is an integer. And the last one is, let's say I gave you f of x is x to the square root of 2. The first is, what the hell does this even mean? What does it mean to raise something to the root 2 power? You say, well, maybe I do it as an approximation. I do x to the first, x to the 1.4, x to the 1.41, x to the 1.414, taking more and more digits. What we really want to do is we want to write this as e to the g of x, because we know how to differentiate the exponential function. So if I take this, I would take the natural log of x to the root 2 is the natural log of e to the g of x. This is root 2 natural log of x equals g of x natural log of e, which is just g of x. So x to the root 2 is just e to the root 2 natural log of x. So the derivative by the chain rule is e to the root 2 natural log of x times the derivative of root 2 natural log of x. What's the derivative of root 2 natural log of x? It's just root 2 times 1 over x. But this part over here is just x to the root 2. So it's x to the root 2 times root 2 times x to the negative 1, or root 2 x to the root 2 minus 1. And so this is how you would take the derivative of something like x to the root 2. And what it means, and we'll stop, is e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. It's the sum and goes from 0 to infinity of x to the n over n factorial. And this makes sense for any input x because we're only raising it to an integer power. All right, so this just gives you a sense of how you need to do things carefully. This is a good place to stop. So if anybody has any